In the last video, we saw some of the differences between hard links and symbolic links. We saw how hard link is a copy of an entry in the inode table or the inode block, and it points to the same disk blocks where the contents of a file is stored, as opposed to a symbolic link. What you have is a new entry in this inode table or inode block, which points you to some block which all it contains is the actual path of the file, which will point you back to the inode table entry for the original, for the source, and then that will tell you where the contents are. So if you were to access a symbolic link, you'd have to go through this inode table, find this actual path, then it takes you through the inode table to the actual data. One of the advantages of soft links or syncs is that you can work between file systems. So if you have two actual hard drives on the same system, you cannot have hard links, because hard links only point to data blocks in the same file system. Whereas symbolic links, for example, let's say you have a source, it's on one hard drive, and it points you to the actual data is stored here. Well, you can have a symbolic link that's on a totally different hard drive. It will have a disk block address, which contains the complete path, and that can be on a different hard drive, so that you go to the inode table of a completely different hard drive and then access the data from here. So even though there's these different levels that you have to go through for a symbolic link, it has additional flexibility that you can go between hard drives, between physical hard drives or logical hard drives. Okay, so all of this stuff is sort of hidden from you. So keep in mind that all of this is not actually visible in user space. This is all all of this structure that we just looked at. It's just an illustration to show you that this is all done in kernel space. In kernel space, you keep track of all of these things, like the actual entries in the inode table, all the different fields, for example, the permissions. You cannot set this in user space. You have to go through some system calls if you want to change things like this. And so there's different levels that you have to go through, levels of software, and that's really why we looked at that first slides that show you all the different levels between hardware and user programs. Okay, so let's say we are in user space. That is, we're restricted to the users' programs, data and files, and so on. We can write a program to read, let's say, 100 bytes from a file that's named X, let's say, into a buffer area. So this read function is part of the C library, and the C library read function will actually make a call to a kernel C function. So not every, but a lot of the functions that we will use, for example, the read, it's called a system call, but really all it is a C library function which goes through a few layers of software in the operating system, eventually gets to some kernel code, which will then manipulate these structures, that is, this file system structure. Okay, so that sets the stage for looking at some of these basic file functions. The ones that we will be using most is open to open up a file so that we can read from it or write to it. We can also use create, which is like open, except that if the file exists, its contents are sort of erased or truncated. That is, if you have the file, it already exists, and you use create instead of using open, then basically the file is erased. And then the other opposite of open or create is close. That is, you say, okay, I'm no longer going to use this. Then the kinds of things that you can do are read from the file, write to a file, move around in the file using the lseek function to, let's say, move to the 10th byte or the 100th byte or the 10,000th byte. So now all of these functions, these simple functions, hide all of this complexity that's involved in going to the actual data itself. So although in this, when in our programs we just say read 100 bytes, there's code in here in the kernel level that goes through all of these data structures, finds the actual location of the disk blocks, and then these 100 bytes, for example, may be on 2 different blocks, and you don't have to deal with any of that in the user code. All of that is taken care of in the kernel section of the read code. So there's also some other file functions that we will not use that much, but they are available. Unlink, all it does is remove a file. So you just call unlink with file name, and it removes the file. Remove is the same as the unlink. Unlink is usually what's used, but you can also use the remove function. And then there's fcntl, which changes the attributes of a file. What are attributes of a file? It's all of the things that go into here. All of the things that you can access using, for example, the stat command or the stat file system command. So let's take a quick look at fcntl. There's a bunch of things that we can pass it. So you have to open a file first, and fcntl acts on an open file, fd, so whatever this fd is. Once we've called the open or the create function, we have an open file. After that, we can call fcntl with the first parameter being the return value of open or create. And then the second parameter would be a command, and you can also pass it's overloaded. You can have other function parameters, such as you can pass in a pointer to a struct. Well, we'll talk about structs in just a second, or you can pass in a long argument. So the fcntl function, like a lot of system call functions, returns an int, and if it's negative, it tells you that that call to this fcntl did not work. And the return value, if it's not a negative value, is the result of executing the command, the cmd, whatever that is. So here's a simple example. We just say we open a file, assume that this file has been opened, and let's see. So to do that, in main we have to say fd is equal to open, and then pass in that fd into this one of our functions, and then that goes into fcntl, and we use a standard command. There's only a finite repertoire of commands that fcntl can execute, and this is one of them, get file information. So this is basically the same as the stat command. And so once you execute this fcntl command, you will get a whole bunch of information that you can then decode in this program. Okay, so that's just an illustration to show you how things work, how low-level system calls are made. And the next thing that we want to look at is structs in C, which we've looked at before, but let's take another look at using structs. And we'll do that in the next video.